So, hello, my name is Frank Kirchner. I'm the director of the Robotics Innovation Center at Bremen and the professor for robotics at the University of Bremen. And I welcome you to this competition on the IJCAI 2023 on athletic intelligence. I was asked to give a few introductory words on robotics and artificial intelligence, trends and impacts, and I'm happy to do so. So, in robotics, actually, it's important to understand that artificial intelligence is actually something that has been thought about already early last century by the father of computer science himself, Alan Turing, because in his paper on intelligent machinery, Alan Turing already argues that if we wanted to study artificial intelligence, it would be best to build robots. And for these robots, he had a couple of requirements that he formulated. So first of all, they should be complex kinematics. So a complex kinematic structure that enables these robots to interact with an environment in a very structured and very deep way and a deep sense. So a high disposition of interaction with the environment, which means, of course, complex kinematic structures, fingers, arms, legs, and so forth. They should also be equipped with lots of sensors, to perceive the environment in the most comprehensive way possible. And then he argued that these robots should be interacting with a real-world environment. So explicitly, focus was interaction with the real world. And the reason for that was that he said that many of the things that happen in the real world can simply not be covered by simulation. So there is uncertainty in this environment, and this uncertainty is something that the robot needs to learn to cope with. Not necessarily to control it in a classical control theoretical way, but to cope with it, to manage these uncertainties, these pitfalls of the real world, so to speak. And therefore, and that's the fourth claim, the robot should comprise a learning mechanism, a mechanism that learns from the past interaction with the environment and then improves on its behavior. And finally, Turing claimed that this learning mechanism should be open-ended. So it's a learning process that you start, but there's no defined end to the learning process. So it's an ongoing process of the robot interacting with the environment, learning from this interaction, improving its behavior. And by this time, the robot will be able to reach a level that humans might call intelligent. So in a way, basically, even though Turing, of course, was one of the greatest mathematicians of the last century, he claimed that we need an iterative approach to approach artificial intelligence by using robots, but there's no single line equation that you can formulate in order to create artificial intelligence. And this was covered here also by other people interacting with Turing, for example, in what were called dining clubs, where people from all different fields of research basically met, and things like the TurtleBot came about. So the TurtleBot here is a very simple robot, actually created by Gray Walter, who was an EEG researcher, not at all a roboticist, but in these communities that formed here, they got these ideas and created, for example, what's called cybernetics today. So the interaction between mathematics and biology. And the TurtleBot here is a little example of this. Here's a picture of it actually with a long exposure, so you can see the little light as it's walking around or driving around this dark environment, finally ending up to drive into his little charging station. And then without even knowing, of course, about it, it was recharged. And as soon as the battery power got back to its normal level, the behavior of the TurtleBot would switch to avoid the light, so it would automatically drive out of the little garage there and then continue to wander around. So it's a very simple robot which has lots of similarities with current robots that clean our carpets at home, or that mow our lawns in our gardens. Very simple behavior. And based on this, I think it's important to understand that artificial intelligence has always been an interaction between engineering science on the one hand and neuroscience, biology, even linguistics and psychology on the other side. And in the heart of it, there's of course computer science bridging these two sides of the river anyway. As you may know, that linguistics created a big deal of what is today modern computer science by Noam Chomsky's hierarchy of formal languages, so the so-called Chomsky hierarchy, which is the basis for all even modern programming languages that we have. But also neuroscience, biology, that feed into cognitive science, and at the heart of this is actually artificial intelligence. So this junction between the two fields is very common, it's actually long been understood as such, and it's now becoming more and more practical as we can improve much on the technical side of our robotic systems. So to bring it together, basically this is the formulation of the robot problem as it was presented by Turing. There's this robot with this high degree of complexity that is living, so to speak, in a natural environment, and it perceives this environment, and it tries to find appropriate actions to improve its behavior. And every once in a while there is the signal coming from the environment that's saying that something was good or bad, you know, this reward signal. And all we need to do basically is find this function that maps from perceptions to actions, and because we want to know what are the optimal actions in all moments of time, of course we have to work with expectations, because we don't know, we cannot fully analytically describe the environment, nor the robot for that sake. So we have to work with expectations about how we believe that a certain action taken at a certain moment in time will actually pay back. You know, what will be the long-term average reward that I will receive if I take an action now in the near or far future. And that's basically formulated and packed into a function. Some call it the Q function, value function, whatever you name it. Basically, the idea is to grasp this value of expectation about how valuable, how good is a certain action that I take now for my long-term expectation and reward. And based on that, you can then formulate a policy that allows us to always pick the right action, the optimal action at any given moment in time. So that's basically the theoretical framework as it was also already proposed by Alan Turing. Now, if we look at actually creating such robots, and by the way, Turing explicitly also in this paper said that this is probably a great idea, but unfortunately we cannot do it because in the 40s of last century we didn't have the technology. So our motors were much too big, the sensors were way too low in resolutions, and no digital communication channels and so forth. So the technology wasn't there. But today I think we have the technology, and we're still faced with these four major challenges. There's the structural complexity. As I said, Turing wants a very highly structured robot that is capable of interacting in a variety of ways with the environment. And that's a good thing, but of course you need to control it in some way. And that's becoming more and more complicated, as you will also learn during this competition. The more degrees of freedom you add, the more complex does the control problem become. And at some point, actually, the algorithmic complexity obviously is rising with every degree of freedom we add to the system. So we have to think about frameworks. We cannot just write one big program. Now we need to order our program. We need to create frameworks in order to handle the algorithmic complexity. And in some extreme cases, actually, and that comes very quickly with adding more and more degrees of freedom, even the classical control approaches have their problems and limitations, and that's why we have to resort to learning. So we are imposing and applying more and more learning methods, also data-driven learning methods, in order to handle the kinematic complexity of such a system. And once we've solved that, then we can, move forward and try to use it actually in what Alan Turing wanted it to be used in the first place, namely a natural environment. And then what happens usually is this moment you bring this system into the natural environment, it fails. And you see that you need another degree of freedom here or another degree of freedom there, or more sensors here and there. And basically you have to go back to the lab and start all over again. So in 2 dimensions, this looks like we're turning on a circle, turning on a spot, but in fact, it's not only 2 dimensions, it's a 3-dimensional problem. So we are looking at walking on a spiral upwards towards more and more complex, more and more capable robots with every turn we make on the spiral, because the robots are getting better, technologies are getting better, and we are making more progress also on the algorithmic side. So that's the good news. Anyway, if we look into the far future, we want, of course, having learning robots in human environments. We want robots to directly interact with human beings. That's why they need all this kinematic intelligence. We want them to actually learn from humans, because some problems, like here in the upper right picture, even though they sound like trivial for a human being, like packing a shoe in a shoebox, if you actually look at this problem, it's something that is very hard to describe, if not impossible to describe formally. So we're approaching ways like learning from looking at humans performing the job. And in the even more far future, these robots should even be able to, let me say, to read our minds. Like if you interact with a human counterpart, you have some capability to predict what the intention of your counterpart is. And that, of course, facilitates the interaction between humans. And it should also be possible for facilitating the interaction between humans and robots. And here in this video of Boston Dynamics, a famous video, you can see some of the best examples of what I would call kinematic intelligence, without actually this kind of high-level intelligence that we already would expect to see in such robots. But you can see very, very well that having a very sophisticated structure of such robots, you can handle things like this, when you stumble, when you fall, walking over the snowy ground, uneven terrain. And that doesn't mean that there is some high-level planning involved here. It's just the basis of simple kinematic intelligence in conjunction with sophisticated control structures. So embodiment is a major player in this whole game. And for embodiment, of course, you need intelligent actuators. So here's an example from the DFKI that we worked on over the last 20 years, to create very small, powerful packages for actuating systems, including the power electronics, the communication channels, of course, the motor, brushless, of course, and the gears still, unless we find ways to replace the gears. But in these last 20 years or so, we have created such a thing that can now be used in many different geometries of robots, like you see walking machines, driving robots, even exoskeletons, humanoid robots, and so forth. So the hardware is a major part. Another part is intelligent structures distributed all over the robot. So here's an example of a foot that we have created. And as you can see from bottom to top, it's created by several layers, and the important layer here is this sensoric material in the middle called Zuflex, and that's a material that reacts against pressure and gives you a signal up from it. So we decided to put it under the soles of our robot in order to make the foot small, but get the appropriate information that we need in order to control the balancing during walking and standing of the robot. So this is what it looks like in action. So you can see the guy here in this video pressing on the foot, applying forces to the foot. And in the back, you see these blue dots that are lightening up when there's a certain pressure inflicted on this point. But what you can also see is that there's many dots lightening up. And in order to not to send all these informations from each single pressure point in the sole of your foot up to a higher level computational center. We've created a system that will immediately in the foot compute the center of pressure and the center of gravity and mass for the robot, and then just send this signal up. So what we're basically doing is, instead of running like 40 wires from the foot all the way to the brain, we're just running one wire that carries the appropriate and important information needed for high-level control structures. That's what we call local intelligence. And local intelligence plays a major role if we actually want to make use of some of the concepts that we know from biology, for example. So there's this concept of the efference copy. That's basically a concept derived by nature, saying that my high-level brain knows that now I will be walking over a flat ground, so I can send a signal down to the local centers saying, okay, what you have to expect in terms of sensor values for the next couple of minutes or so will be within a certain range. So don't expect any pikes and any spikes or something. It will be rather smooth, pressure values, for example, coming from the soles of your foot. And then this stuff is done decentralized, while the higher levels can continue doing something else, for example, giving talks, stuff like that. So once we have such a local control structure, then we can implement it all over the body of our robot, and then we can even, as you see in this video, do things like this, where a four-legged chimp-like robot, in this case, is actually managing to stand up based on its 2 feet, just on the hind feet, and then do some balancing behavior and so forth, and even start walking on the two legs. So the transition from four-legged walking to two-legged walking can be facilitated by such a distributed control approach to a large extent. And what's more important, it's much easier to debug the system, because you have the local controllers that you need to debug, rather than one big monolithic control program. So kinematic intelligence can be, or should be, must be a basis for higher level autonomy. And so there are some examples that you can see here in this video, like this guy to the left that's just running crisscross over this terrain without, of course, knowing anything of what it is doing. It's dumb like a rock, but it can manage to cross this environment based on its kinematic structure, based on what I would call kinematic intelligence. On the right side, you see then the same system basically equipped with high-level intelligence, and that can then be used for navigation in unstructured and difficult environments. So one more example that I would like to show you here is actually from a very early work. So here you can see what kinematic intelligence can look like. You have this robot with springs attached to his feet, and you can see how this already saves, for example, lots of the energy. You can use kinematic intelligence also in a different way. So you see this six-legged robot, and the guy is flipping it upside down, and what the robot does is just flipping its legs around and then continues to walk. Or you can do things like this, combined with a control structure already. The robot here carrying this piece of wood over a lock, without, of course, knowing that it is carrying a piece of wood, by just using one of his 8 legs to hold the board, and then use the other 7 remaining legs to walk across this big board. Or you can do fancy things like this, if you need to cross a ditch, for example, and there happens to be a lock over the ditch, you can use your kinematic structure in order to overcome this obstacle. And then even if you look at this one here, lower right, you can easily, play with walking possibilities, from walking straight forward via a lateral walking into a complete sideways walking. So a diagonal walking into a complete sideways walking. So that's all stuff that's plays into the field of kinematic intelligence, and the videos that you just saw were from like 20 years ago already. So this is a big body of work that has been done about this. Now we can use it today, 20 years later, and we can apply it and support it, for example, navigation problems, so-called SLAM approaches, simultaneous localizing and map making, by using these kinematic information, tactile information, for example. As you can see here in this video, the guy is running around in this previously unknown environment, and then using classical SLAM based on camera data, but fusing this camera data with tactile data coming from its structure, from its kinematic structure that works for legged systems or for wheeled systems, just as well as you can see in the right picture for legged systems. And that can lead to a great improvement of the reliability of these maps that come out of this robot. So with these words, I would like to thank you for your attention. I wish you a great competition and a great success with this workshop, with this competition workshop here at the IJCAI 2023. Thank you very much.